1, 2, 3. Hello, everybody. Let me see if I can share a screen here. I know, Sharon. I am so sorry. I am. I had a hard day. But yeah, it's so weird because I've been there faithfully, the whole hour, just pure silence for the last few days, and then today, two people came, and I was like, oh no. But there were questions about the crystal violet report, and I can answer those questions really easily for you anytime. After a lecture, for example, or by email, or tomorrow, or whenever you like. Do you have a question about the crystal violet report, Sharon? Okay, cool. You'll stay after class. Perfect. Okay, that works. Excelente. Can you guys see the screen here? The standard edition screen? Yeah. Okay. So I promised last time that I would talk about the different methods that we use to validate methods. So the different approaches we take to that. And so what I'd like to do is I want to insert some slides here, and I'll write on them. I'm not sure if I can do that from this place. Maybe if I go through this guy. If I do, I don't think it's going to let me edit from here. So I'm going to have to stop the show, I think, and then add a page. Come down here. New slide. Delete some of this stuff. Then I'll go back to this guy. So let's talk about how do you know if your method is valid? How do you know that it's telling the truth? Oops. Right? Valid means truthful, basically, or accurate. You know, you can often measure precision, and precision and accuracy aren't there together, of course. But accuracy, the best way to measure accuracy, right, is from a standard reference material. Which is a commercial thing that you get from, you buy it, right? And they exist for lots of different things, and you buy them from the NIST, the National Institute for Standards and Technologies. And what you do is you analyze the reference material, and you get a, let's say you get a, lead parts per million with your method. And then you compare your method, you compare your answer to the standard reference materials known concentration of that analyte, for example. So you get sort of like the PB according to you, and then you can compare that to the lead according to NIST, and you can do this because the material, it's a standard reference, and this is known as accurately and precisely as we can know it, as human beings can know it, right? So failing this, right, then what can we do? Well, this is the best way. But for example, if you've got arsenic in a corpse, or you've got chloroform in a brain, or you've got arsenic in drinking water, you could definitely do. But there's many settings where standard reference materials don't exist. And so in that case, if you don't have a SRM, then you've got a number of tools at your disposal, right? One is spike recovery analysis. Right? And to do spike recovery, this when you recover a spike, that means you've added intentionally some analyte into a sample at an early stage, right? And then you carry that sample through the preparation steps, and it could be digestion or extraction, or it could just be directly measuring it. But whatever the steps are, you carry the spiked sample through the preparation method, and then you measure the amount of analyte in it, right? So the spike plus the call it the native analyte. This is what ideally you will measure. Right? And this way you can develop a spike recovery, right? The percent spike recovery is equal to the milligrams found minus weight. Right. The milligrams in the sample divided by the milligrams spiked times 100%. So in this case, the milligrams found equal the milligrams in the sample plus the milligrams in the spike, right? But found through your method. Right? And then the milligrams in the sample, you have to have independent knowledge of this, right? Oops. So in this way, what you're doing is you're comparing the milligrams of spike that you found over the milligrams of spike that you know you added, right? So the spike recovery, that's the milligrams found over the milligrams added, right? The milligrams found from the spike, right? Of the milligrams added there. And so this tells you about what part of your experimental process. I want to pick on somebody. Can I pick on somebody? Or actually, do you want to think about it and in a breakout room for a couple minutes and then answer the question, what part of your analysis does spike recovery validate? Right? What part of your analysis does it actually say, well, this part of the analysis is correct. And Snigdha says the analysis. Hold on, let me catch up on the chats here. Yeah, so the lab report is due tomorrow. Yeah. So in order for the spike recovery to come out correct, right? What does that, let's say you did a, yeah, it's accurate, right? Let's say that you did this vitamin tablet experiment, right? And you analyzed the copper in a vitamin tablet, right? And then you added a milligram of copper and you analyzed it again, right? And the first time you got 0.75, and the second time you got say you got 1.5, right? Let me write that down for you. Actually, I need another. Oops, that's not right. Oh, that's kind of cool. I can write on this, but it's not going to save anything. But let me try it anyhow. So let's say you, whoops, and now it's going to go away. So yes, I'm going to keep them. Okay. So let's make another one here. Nope, not like that, not like that. Okay, so you have a vitamin tablet and you analyze it and you get 0.75 milligrams of copper. Then you take a second vitamin tablet and you add 1.0 milligrams of copper and you analyze it and you get 1.5 grams of copper. Well, the spike recovery percentage there is 1.5 minus 0.75. Oops. Divided by 1.0, right? That's the amount. This is the amount that was there. This is the amount that you measured. This is the amount that you spiked. So, and it's times 100%. And this is equal to 0.75 over 1.000 times 100% equals 75%. So now the analyze here, what this means is that you you digest in 4 molar HCl. You do a quantitative dilution. You centrifuge and you aliquot. and then you measure this. Right. This is what measure it against standards, you know, versus standards on the MIP. Right. And this is all called sample preparation. Right. So what part of this, or why was this less than 100%? Maybe where can we lay the blame? Yeah, it could have been the aliquoting. It could have been the digestion made a volatile copper product. Seems pretty darn unlikely to me, but who knows? You know, copper chloride, maybe if it's boiled too hard, you lose a little bit of copper. The centrifugation could have been a problem, right? But in general, what this is all part of the sample preparation, right? So when you do a spike recovery, if you don't get 100%, then it's likely there's something wrong with your, then your sample preparation is invalid, right? And you have to ask yourself, how much error you can tolerate, how much loss you can tolerate, how much, like maybe you do this and you get you know, 163% very consistently, right? Then somewhere along the line you're picking up copper. It could be in a pipette or in the centrifuge or something like that. So that's more, it sounds more likely to be in an ultra trace analysis, but it can definitely happen, right? So, so one way to validate your sample preparation is to do a spike recovery analysis, right? So there's another problem that can come up in an analysis like this, which is a problem with matrix effects. Okay, so let me see here. So I'm going to add another slide. Back here. So the matrix effects, oops, it's not too, there is it. The matrix effects are changes in the instrument response basically due to the sample matrix. Sample matrix is the solvent and other solutes that are not the sample. Oops. Oops, what just happened here? Uh-oh. Computer's not answering. There we go. Yeah, there we go. So the solvent and other solutes can affect the response. So it's like if you have a calibration plot, signal versus concentration of your analyte A, it might look like this when it's done in, say, 1% nitric acid, but it might be more like this when it's done in, let's say, seawater. Right? So it's not always easy to tell if this is happening, right? You can't, it's hard to know what the other components, how they're affecting an instrument. So let's say you have a beaker and you have a tube going into this beaker and it's going through a pump. That pump has little rollers here. And this pumps a flow to an instrument. And the instrument then makes an aerosol. It makes a lot of fine droplets. And then these droplets are passed onto a plasma. Right? Oops. Come on. There we go. You got to go left and right here. So in this case, what qualities in this solution could affect the pumping rate or the droplet size? What type, oh no, the viscosity, absolutely. The viscosity. It's not stupid at all. It's actually the answer that I was looking for. So viscosity has a profound effect on any atomic spec method where you are, where you essentially nebulize, that is, you break up your sample into small particles and then pass those particles into a plasma. So in that case, you know, this change between nitric and seawater, this could have to do with viscosity, or it could have to do with pH, or any number of different factors that all of which go into the formation of these excited state atoms inside the plasma, right? So if you want an accurate, if you want a very accurate atomic spec, then what you need to do is to do standard additions. Right? And in standard additions, in one type of standard additions, you split your sample into let's say 5 flasks, and you put a little bit of sample in each of these guys, right? Put the same amount into each one, right? And then this one, you simply dilute to mark with some matrix that is favorable to your analyte. So like 1% nitric acid is real common for metals because none of the metals precipitate with nitrate, right? So then to this one, what you do is you spike it with a small amount of standard. Then you dilute it to the mark with nitric, and then you use a little more standard matrix, a little more standard, some matrix, a little more standard, and the rest matrix, so that you have 0, 1, 2, 3, and 4 parts per million of added analyte. Right? And then when you measure them, all of these are in approximately the same matrix, right? Okay. So does this make sense that when you do this, the matrix effects are largely canceled out? So who can explain to me why standard additions cancels matrix effects? So let's see. Why don't we take a minute and let's see here. I think I can set up some breakout rooms. Oops. Breakout rooms. I'm going to create say 5 breakout rooms. And I'm just going to create them and assign folks to them automatically and open them. And what I want is for someone to explain how standard additions compensates for matrix effects, how it makes the matrix not matter. Okay. Hey guys.
Hi.
Hi. So how does this matrix stuff get canceled when you do standard additions? Or what is a matrix effect? Who here can answer what a matrix effect is?
Is it like the stuff in the compound interacting with it?
Mm-hmm. It's the analyte.
But is it that's interacting with the spike specifically? Like
Okay.
okay.
Wait. So the it's actually very closely related to spike recovery, but we don't describe it as spike recovery. And what interacts is something about the matrix, which is what?
I'm not sure.
Okay, so the matrix is everything in the sample other than the analyte. The analyte is like a needle in a haystack, right?
Okay. Yeah.
And then there's all the hay, right? And the hay can have different metals and different components, right? And sometimes the metals can interact with the hay in a way that changes the instrument response.
So the matrix.
Right. Exactly.
Okay.
Exactly.
So it's just basically another name for like a sample spike, kind of.
So you could say that. Right now, what I want you to focus on is how the method of splitting the sample and then adding a little bit of standard, and then a little more standard, a little more to each of a series, and then analyzing that entire curve, how that tends to cancel matrix effects. So if you guys could discuss that amongst yourselves for a couple minutes, and I'm going to visit some other rooms. Okay, and even if all you come out from this is like refining your definitions of like, why it's more or less sensitive, or, what more or less sensitive means, that type of thing, that's fine. Okay. Okay. All right. I'll be back.
Hello. Could you
Hey,
be able to
Daisy.
assign me to a breakout room?
I got to assign you to a breakout room, don't I?
Yeah.
Let's see here. I don't know how to do that. Oh, there's only, let's see here. Assign to, how about room 5? There you go.
Thank you.
Okay, cool. Hey guys.
Hello, Professor.
Hello, hello. So what do you think? Is the question too broad, maybe?
I think a little bit. I think like, are you asking us how this like the standard edition removes the matrix effects, or like how it
Yes.
works altogether?
Yeah, how it removes matrix effects.
Is
That,
it
yeah. Mhm.
is it because like one of the sample isn't spiked, so like we have our like standard and everything else is spiked with like all our known analytes and like we dilute it all so like we're changing it up each like vial individually.
Mhm, mhm. Yeah, that's really close. So if you measure your standards all in nitric acid, and then you measure your sample in seawater, will you get the right answer?
No, because of different environments.
Yes, exactly.
So could it be because they're all measured in the same exact environment that the matrix effect gets canceled out?
What do you think, Snigdha? Joanna? Do you have an
I think
opinion
that
here?
kind of makes sense with the whole
Mhm,
being in different environments.
mhm. Yeah, it makes sense to me, Logan.
Yeah, that makes sense.
Okay, so can you paraphrase what Snigdha said to me then?
Me?
Yeah.
Yeah, so she was saying that like the two different things like the seawater and like the nitric acid, they can't be, I forgot the word, but like because they're in different environments.
Mhm.
So then that's when they would be measured in the same environment, that's what would cancel out the matrix effect.
Right, right. All you got to do is make the environment the same, right? And by adding by taking a small amount of sample and adding a small amount of spike or of standard, right? You could call it a spike or standard, right? And then even if you add 1, 2, 3, 4, and 5, it's still a small amount relative to the total, right? And when you measure it, the matrix is approximately the same. Good, you guys did good. Okay, I've got to find, I think I'm probably going to assign this to one of y'all to explain to everybody. So choose a victim. Okay. Okay, how do I get to the breakout rooms here?
Validate that, Matt. Yeah, I think so, because like I'm looking at it and like people spike it with different amounts, so it looks like it's like an internal calibration curve, like while
Yeah,
you're
'cause
doing the sample.
well, no matter what you like put the matrix in, they should all have the same matrix effect. So I
Right.
think it's you have two, you have you compare it to the curve, because then you go back to where the x-axis is at, and they should both be at the same x, which tells us our unknown concentration.
Yeah, that makes sense.
Marissa? What think you, my dear?
Yeah.
Yeah?
Yeah. Hey,
Well-
Professor, I had a question real quick that's a little
Yeah.
bit off topic, but
Okay.
did you upload the UV vis data for the Tuesday lab yet? I think I sent you an email, but I didn't see it on Canvas.
I think I did, but I'll check.
Okay, thank you.
Yeah. Gentlemen,
Yes,
do these guys make sense to you?
I can follow their logic just fine.
Excellent. Excellent.
Yeah.
That sounds good. Okay, cool. Think I'm gonna leave now, and I will. I think I'm gonna close the breakout rooms. So. Hey guys,
Hello.
how's it going? Good or not so good?
Just okay.
Mhm.
Yeah, just okay.
Okay. So the idea here is sort of thinking through this standard additions, right?
Yes.
So what problem does standard addition solve?
It helps resolve accuracy of results.
Exactly, exactly. And the type of inaccuracy is due to the matrix effect, right? Now, what is the matrix effect specifically? Gerardo?
Yes, sir.
What's a matrix effect?
What's the matrix effect?
Yeah.
Let me look at my notes.
So the matrix effect, it's like at the heart of this question, right? And it's what. So let me ask you in a different way, right? If you analyze for copper and you calibrate your instrument using copper in DI water, let's say, copper nitrate in DI water, right? Then you analyze for copper in seawater, a very different matrix. Will you get the right answer?
No, because there's two different things going on.
Right, right. Gerardo?
Yeah, I see what you mean.
Yeah?
It would be two different examples, essentially, right?
Right, right. They're two different matrices.
Right.
Yeah. So, so when you do standard additions, what is common between the standards and the samples?
The analyte? No.
Yeah, the analyte's common. That's true. That's not exactly what I'm looking for. But there's two parts. There's analyte and there's what? It starts with an M. The analyte is dissolved in seawater, right?
Solvent.
Solvent, right? Yep. And the solvent and the seawater and the sodium chloride and everything else there is part of the what?
Matrix.
Yes, the matrix. Excellent. Morpheus would be proud. Excellent. So the difference in the calibration between the seawater and the pure water is a matrix effect, right? Because the only reason it's different is because of the matrix. And if you need them to be the same, so you can analyze your sample accurately, then you use what method? Okay, I'm going to leave you guys with that question. What method do you use? Hey guys.
Hello.
Hey.
Hey, how's it going?
Good, good. How's it going with you with this question?
I think we got it.
Yeah? Cool. Tell me the answer.
So we were talking about like when there is a matrix like in your sample, like it
Yes.
causes a lot of noise and
Yep.
like the accuracy diminishes a lot.
Exactly right. Exactly.
And so by adding a spike and then like diluting it and then adding more spike and diluting it, like it allows the curve to become more accurate and like you're only getting the signal of your analyte. So it kind of like diminishes the matrix effect.
Right, right. So Kiara, does that make sense to you?
Yes, it does.
Okay, cool. Excellent. So there's one slight tweak that I'd like to make to that explanation, which is that it's not that the matrix is adding noise.
Okay.
It's that it's changing the response to the analyte, right? And usually it depresses it, right?
Okay.
So the sodium chloride will mean that 1 part per million of copper gives a smaller signal than 1 part per million in water, right? Like the seawater, the other parts of the seawater will give you a lower signal per unit copper.
Okay.
Right? Excellent. So that is called matrix effects. And what fixes matrix effects?
Standard edition.
Standard.
Yes. Yay. Cool. Excellent. Excellent. Cool. Okay. We're done with this now. So cool. All right. So it seems like we are on the same page now in terms of standard editions, right? And the problem that you guys may face is that the calculations are a little bit picky, right? When you talk about these equations here, oops, sorry. And I'm not going to go over them because I just get tongue-tied and it's kind of hellish for me. So there are a couple questions on this in the homework, but there will be no questions, quantitative questions on standard additions on the exams. Okay. And standard additions will be covered on the midterm, but not on the final, right? So the midterm covers up to the first half of the class, and the final covers the second half of the class. So just so you know what's going on, right? But anyhow, so what I was getting at earlier, let's see if I can find my, I think I'm going to try and find my notes there. There we go. Add them up here, right? This was this is about standard additions, right? Oops. Writing all over the place here. So this was oops. And that fixes the problem of matrix effects. All right. So we've got spike recovery. Standard additions. Then we've also got a thing called internal standards. So I'll just go over the slides here for standard for internal standards. By the way, this is how I like to do standard additions. And I can, gosh, that's fairly easy one to describe. I'm just not prepared right now. But internal standards here, there's like, you know, in general, there's like, sample prep, and then there's sample matrix, and then there's the instrument. And these things overlap a little bit in the analysis, right? The sample prep you can validate using spike recovery. The sample matrix effects, you can use standard additions. And the instrument, and let's actually be more specific here. Eraser. This is called instrument fluctuations. Right. And so an instrument fluctuation is a bad thing, right? So there's little fluctuations little random fluctuations. We refer to these as noise. And then there's other kind of things, right? You can have kind of basically electronic issues or mechanical issues, you know? Or maybe optical, maybe some something got on a lens or a detector, you know? And like, you know, for a constant sample input, you get this fluctuating signal. That's noise. You can make it smaller sometimes. Sometimes you can't, right? And you know, hopefully these electronic, mechanical, and optical problems don't come up. But what if they do and you don't know about it, right? What if you measure your samples or your standards when the signal's up here and your samples when the signal's down there? Right, that will give you the wrong answer for your analyte concentration. So in order to deal with that, what we do is we use internal standards, right? And an internal standard is a known amount of a compound that is not present in the sample standards or blanks, right? It's something foreign. So let's say a rare foreign compound, right? And it's not normally present. It's not present in the blanks, not present in the matrix, not present in the analyte. So an example that's often used in atomic spec is lanthanum, right? It's not super rare, but it's, you know, normally not present in water or acid or, you know, samples. I mean, if it is in your samples, then it's not a suitable internal standard, right? But for example, lanthanum. And so the idea is for an internal standard that the internal standard, oops, I gotta get some shot here. So the internal standard here is readable on a different frequency of the instrument. You can tune the instrument differently so that it doesn't see your sample, but it does see the internal standard, right? So, oops. So the instrument must resolve the sample, any interference, and the internal standard. right? So, so that means that you need to have an instrument response that's a spectrum. A spectrum can be absorbance versus wavelength. It can be emission power versus wavelength. It can be signal versus M over Z, the mass to charge ratio of an ion. And it can be signal versus time, for example, in a chromatogram. Yeah, does that make sense? So now, an internal standard, right? It compensates for variation in the instrument for variation in the instrument response from run to run, from moment to moment, right? It's normally a temporal change. Or a temporal fluctuation, right? And I completely disagree with this statement. And it is helpful if the internal standard is chemically similar, so that the effects of matrix can be minimized. But it's not crucial that they be absolute minimum. They just have to be consistent. Right? So an internal standard here in a chromatography experiment where we're looking at signal versus time here is a resolved peak, right? It's a peak here that is different from our analyte. There's our analyte. And this is our internal standard. Right? So the idea is that if you do a bunch of chromatograms, do 10 or 20 or 30 chromatograms, and they all have the same amount of internal standard, then this peak area, the A sub S, the internal standard signal, right, will be the same in everything. Right? So if your instrument screws up in some way, if your instrument fails in some small way, then the internal standard peak will go down. Or if it gets better somehow, then the internal standard peak will go up, right? But since you know its concentration and you know its signal, then if the signal goes down for the internal standard, you know to expect the signal from the analyte to go down. Right? So let's see here. Let me try to give you an example here. I'll just write on the screen right here, but if you have, I have to do there's our IS, here's our analyte, right? Then we go, here's our analyte, here's our IS. Then we see a third one there. Right? Here's AIS equals 1.0, AIS equals 1.0, AIS equals 0.5. Right? So the area under this peak is the same, then it drops by 0.5. Here's our here's our analyte area, A sub A is equal to say 2.0, then A sub A is equal to 1.0, A sub A is equal to 1.0. Okay. From here to here, did the analyte concentration go down? And from here to here, did the analyte concentration go down? This is a yes or no question. All right. So does anybody know the answer?
Did the first jump go down? I'm gonna say that one's yes.
Yes. And in the second jump?
Is it a no because both of them decreased by half?
Yes, it is a no. Perfect. You guys are awesome. You guys are awesome. So I have to stay on the line to answer a question that I was absent from my office hours. Answer a question that came up in office hours and I wasn't there. So, but the class is officially over, so you can sign off if you want to.
Dr. Tara, I had one question.
Yeah.
Did you happen to upload the data for Tuesday lab?
Okay, I will check on that, and it's possible that the Tuesday lab data is not uploaded yet, but I think it probably is because I went through and I did all that. Let me see if I can.
Because it says it's due tomorrow at 11:59. So I just wanted to make sure.
Oh wow, yeah. So we've got a. So let's see here. I'm going to go to files. Lab. Crystal violet. Thursday, Tuesday. There's no Tuesday files. So what you can do is you can grab any other file. And so I'll go, I tell you what, I'll give you another couple days, but I will put it back. I'll put it in there tomorrow.
For sure. Thank you.
Okie dokie, cool. And who am I speaking with now?
I was gonna ask you the same thing. I didn't see the data and I couldn't figure out the absorbance for the lab report.
Right. Yeah, sorry. Yeah, it's hard without the data. So it's my fault. It's totally my fault. So I will get it there tomorrow morning then.
Does that mean that we get an extension?
Yeah, I'll extend it till Friday.
Thank you.
Okie dokie, guys.
Have a good evening.
Okay, thank you very much. We'll see you soon.
See you tomorrow morning.
Okay, bye-bye.
I had a question.
Yes, Jeffrey.
So for our peaks, which one is supposed to be the absorbance at I max?
Oh, say lambda max, right?
Yeah, lambda.
Lambda max, it's the main peak at lambda max. So there's let's see here.
We have class tomorrow morning, right?
We have lab in the morning, yeah.
Okay, cool.
Yeah, 9 a.m.
Okay, bye.
See ya. Yeah, so Jeffrey, when you plot the data, there's a peak around 600 or 650, I think, and it's the largest feature in the entire graph.
Oh, okay, yeah,
It's
I
the
know what you're talking
highest,
about.
yeah. And so you can take the absorbance, the maximum absorbance from right around that region.
Okay, so mine was at 0.067.
Okay, perfect, perfect.
So then I just upload that to there.
Yeah, so you're gonna upload the entire data set, right?
Yeah.
To,
And
yeah,
then,
yeah.
well, I have it all done. That was the only thing.
Okay, cool, excellent.
Yeah. But the thing is, our final answer for E is nowhere near our like graphed answer.
So
So
so epsilon is
yeah, the
equal
epsilon.
is equal to A over C,
Yeah, A over C.
right? So 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 if when you're graphing it, if it goes up to 0.05 or something, 0.067, then that's fine. That you're plotting absorbance. Then if you divide every absorbance value by C, then it will be, it's going to go up by a factor of 1,000,000 roughly. And then that will be epsilon.
Yeah, because our epsilon for ours was 36,624 plus or minus 1608.
Okay. All right. That's
But
reasonable. It's a
oh,
little
is
bit,
it really?
a little bit low. I think it's like probably closer to 80, but I'm interested to see what happens, because it's not always straightforward.
Yeah, because I was looking at it and I was like, it's nowhere near that answer. Because I understand how we were supposed to do it, but I was like, it's supposed to be near the highest peak, but it wasn't. I'm pretty sure it's because our standard that we made or the solution that we made is probably,
Oh, what do you mean it wasn't near the highest peak? What is that?
well, not the highest peak, but the epsilon was supposed to almost be the same as the graph.
It is.
Based off.
I mean, well, you see the graph, the epsilon max, right? Epsilon max is at lambda max, right?
Yeah.
So if you take the absorbances and divide by concentration, then you get epsilon. And so epsilon max on the graph should match epsilon max in the report. Now, when you get S epsilon max, the uncertainty, that'll be smaller. But epsilon max, and from the graph, you should get it from the graph and put that in the report. Does that make sense?
Yeah, it does.
Okay, yeah, hopefully. Yeah. Anyways, if it's yeah, I can send it back if there's a sort of a flub like that or something, like it sort of came from the left field or something. I'll send it back.
All right, thank you.
Cool. Okay.
Have a good Valentine's.
Yeah, happy Valentine's Day to you too, sir.